Bridges are essential structures that often require balancing weight, efficiency, strength, and cost. Before we can dive into the more complex aspects of a bridge, we must first understand the most fundamental physics principle when it comes to bridges, Newton's first law of motion. Mathematically, Newton's first law of motion is that if sum of forces is equal to 0, then the change of velocity over the change of time is equal to 0. And as a byproduct, acceleration equals 0 for linear motion, and for rotational motion, Newton's first law of motion is where if sum of moments equals to 0, then change of angular velocity over change in time is equal to 0, or angular acceleration is equal to 0. This law pretty much states that the sum of forces acting on an object moving at constant velocity is equal to 0, since Newton's second law states that an object's acceleration is equal to the sum of forces divided by the mass. So no acceleration would mean that no forces are acting on the object, or that the forces cancel out. Same thing applies to rotational, but instead with moments, inertia, and angular acceleration. The meaning of this principle was huge, as philosophers such as Aristotle believed that an external force was required to keep an object in motion, otherwise it would reach equilibrium. This was not the case. The universe does not oppose change in position, but rather change in motion. This is what is known as inertia, which is that objects resist changing motion. This means that mass and moment of inertia measure inertia, so the higher mass and mass moment of inertia an object has, the higher they resist change in motion. The application of this principle has been widespread, as in bridges, you don't want your bridge to be moving, so the bridge must satisfy the conditions of sum of forces is equal to 0 and sum of moments is equal to 0, or more precisely, sum of forces in the x is equal to 0, sum of forces in the y is equal to 0, sum of forces in the z is equal to 0, and sum of moments in the x is equal to 0, sum of moments in the y is equal to 0, and sum of moments in the z is equal to 0, which are often calculated by cross products. If not, then that means the system is unstable and more constraints must be added to keep the system in equilibrium. For our final project, we want a bridge that can withstand 25 pounds of force out of balsa wood without cheesing it with supports inside the bridge, and it must be functional like an actual bridge. Another big factor was material strength. We need to figure out how strong the material is in order to figure out how strong each member should be. After some studying, we came to the conclusion that balsa wood was really good at tension and compression, but really bad at handling bending. This means that we must focus on bending, since that is the stress that will destroy our bridge. How much something resists bending is flexural strength, or what we really care about, the modulus of rupture. It's given by the equation sigma is equal to mc over I, which in most engineering books is not really talked about, since modulus of rupture is a very specific application of sigma equals mc over I, where modulus of rupture is a very specific case that measures the exact stress that causes it to break, and most of the time we don't worry about it breaking, but rather buckling, which is considered a mode of failure. In the general equation, sigma equals mc over I. Sigma is the stress caused by the moment times the distance from the neutral axis divided by the inertia. Even though sigma isn't material specific, the modulus of rupture is, and if we calculate it, then we can figure out the inertia our bridge will need to survive. So how do we find the modulus of rupture? So in my free body diagram, I have a scale on one end and the support reaction on the other, and a force going straight through the middle, and two normal reactions. And the scale reads 30 grams. And in order to find this force right here, we have to find out what this force is. And since it's symmetrical, then that means that this force is twice as much as this one. And all the scale really does is it takes the force, which is equal to the weight, and it divides it by the acceleration of gravity in order to get the mass. And so now that we converted it and multiplied it by acceleration to get this force, we multiply it by 2 to get this one. And in order to find the moment, we're gonna have to section it, which is basically cutting it in half. And in order for this to be in equilibrium, we're gonna have to have a shear force. And the shear force opposes the normal force. And if we're taking moments about A, this shear force is gonna cause a moment. And so we're gonna have to have a moment to oppose it, which is the moment we care about. And so now that we've calculated sum of moments to get our moment, which is 4.6646 times 10 to the negative 2 Newton meters, which will be our m. We're going to have to find the y and I, since those are the things we don't have yet. And since we sectioned it, we have a cross-sectional area of 1/8 of an inch by 1/8 of an inch. And our y is basically going to be the outermost fiber of the wood, because the neutral axis goes straight through the middle, and the point of highest stress is the farthest from the neutral axis, which is this part and this part. And for the inertia, for a rectangle, it is base times height cubed divided by 12, and that should give you the inertia, which tells you how much it resists bending. And for the stress, I have 8.74 megapascals, which is not too far off, since the wood database basically says that the modulus of rupture for balsa wood is typically around 19.6 megapascals. So my value is around half of the expected value, which means that either the density isn't the same or that my values were inaccurate. But I think my values were somewhat correct, since balsa wood does seem to be pretty weak. We now had to figure out what type of bridge to build. Well, it's true that our bridge is technically 3D and the forces may transfer to the other side of the bridge. We are assuming it's 2D since the force is purely vertical along the XY plane, and as long as the out-of-plane forces are small, the effect should be negligible. There are many types of bridges, and out of all of those, we settled on a truss bridge due to how it handles loads the most efficiently in our scenario, and yet there's still dozens of truss bridges to consider. Another factor to consider when designing a good truss is calculating which members to reinforce, which would be the ones under the most tension or compression. I use a site called trussanalysis.com to calculate the forces acting on a truss, since calculating the forces individually on a truss is pretty tedious and time-consuming, and easy to mess up if you forget a negative. And doing it for all the different trusses we analyzed would be pretty inefficient. But the way you solve a truss with method of joints is that even though the truss is a rigid body and not a particle, we can treat the joints as particles, since pins don't carry any moments, and the only forces acting on the pins are tension and compression. There's just one issue. We are building out of balsa wood, so using pins is out of the question, so to hold our members in place, we'll use gusset plates. In real life, pins are impractical too, since pins are often expensive and less durable than gusset plates. And gusset plates try and avoid moments by having all the forces line up and intersect to one point. And since the line of action goes through the point, no moment is created. This means though that the members will have to be perfectly straight and in line to the joint. Otherwise, the force will cause a moment, which is impossible to do perfectly, which is why we have factors of safety. So after comparing all the different types of bridges, we came to the conclusion that the Pratt truss was the best design due to how well distributed the forces and how easy it was to predict which members would be under the most force. The thing is though, we can make our bridge stronger with zero force members. Even though zero force members don't carry any load ideally, neglecting and removing them would be an error caused by our initial assumptions that statics normally operates under, which are: number 1, the members have no weight. Number 2, the loads act only at the pins. Number 3, members are rigid. Number 4, the loading does not change. Even though in our balsa bridge model, the weight is so small that the weight can be neglected, the load changes as we pour sand in, increasing the weight from 0 pounds to 25 pounds. In real life, engineers account for changing loads in bridges by taking into account the most extreme variables, such as assuming all trucks, all buses, all traffic is happening on the bridge. So we want to have some type of factor of safety on our bridge. Also, the distributed loadings create forces not directed at the joints, and members are not rigid and deform easily under force and pressure, and all members will not be perfectly aligned, which will lead to off-center forces that will bend the structure. So by having zero force members, we reduce any buckling that can occur from deformation, creating forces not accounted for, and changing loads. Due to this, we came to the conclusion that the Baltimore truss was the best truss to use. So how are we going to calculate the inertia of each beam? So over here we have a 2x2 inch block, and basically there's a weight hanging from it, which is 25 pounds, which is the weight we want to support, and it's hanging from a 2x2 inch block. So that means that it's going to cause a distributed force on the bridge. And basically what we want our bridge to look like is we want an I-beam with a truss sitting on top of it, and that's basically our design. Basically, we're assuming that each beam can carry half of the weight. So each beam should be able to support 12.5 pounds over a distributed force of 2 inches. Forget that, it should be inches squared. And basically we just divide 12.5 in half to get 6.25 as our distributed force. And that will allow us to calculate the moment, because we know that a distributed force, we can find the concentrated force by multiplying it by the distance that it spans. And so I pretty much got 60 pounds per inch for the distributed force, as basically you have 2 inches spanning on the X direction and 8 inches spanning in the Z direction, which gives us 1.6 inches. And we also have the distance that creates the moment, and if we multiply that by 6, we have 60 pounds per inches. Plug it into this equation, which was the same one we had earlier, where we have the moment, the distance from the neutral axis, and the inertia. And we basically solve for the inertia, and we plug in the modulus of rupture for the allowable stress. And we also plug in our moment, and what we end up with is 47.3 times 10 to the negative 3 C. And so for our C, we plug in a number that we want the height of the beam to be. And I basically got an inertia of 0.0273 inches to the fourth. So we want our inertia to be higher than that. And if we want a little bit of a factor of safety, we can have it like probably double that, just to make it extra safe, which is what I ended up doing. As for an inertia, I calculated this shape to be about 0.0449 inches to the fourth, which is around double that. Pretty much how I calculated the inertia was, since the shape is symmetrical, we already know where the centroid is at. So all we gotta do is use the parallel axis theorem to shift the shapes that are not on the neutral axis. Pretty much after calculating the inertia of each piece and adding them all up, I ended up with this number. So as we can see, the shape satisfies the conditions of being larger than this inertia. So pretty much this I-beam is gonna have a flange of 1/8 of an inch by 6/8 of an inch, and it's gonna have a web of 6/8 of an inch by 2/8 of an inch, and hopefully it can withstand the 25 pounds.